Hello everyone, I'm Sulagna Saha. I'm the Test and Measurement Editor for RCR. Welcome to this session of Industrial Wireless Forum, AI-driven end-to-end network security across IT, OT, and hybrid infrastructure. I'm pleased to welcome Peter Davies, Technical Director of Thales, who will lead this presentation. Peter, thank you for joining us. I'll hand things over to you now.
Thank you so much, and thank you very much for the invitation to be here. Let's see if we can find an arrow to go with this. So I thought I'd be talking a little bit about who I am. I'm a security expert, so apologies. But I do communications. I've been doing communications really for more than 40 years in relation to this and trying to make them secure in relation to that. Lately, I've been leading research activities in relation to autonomous vehicles with their onboard networks, with other things, but also smart factories, and also looking at 5G, and particularly 5G O-RANs and things of that nature to look at how we might defend or not defend those sorts of things. So I hope there's a number of things here that will be of interest. So the sort of questions that have been driving me and that I'll try and cover as part of this is how machine learning or AI is different from your regular complex systems. So taking on board the fact that most systems, telecom systems, have now become ridiculously complex, looking at how that might be the case, looking at where you might be using machine learning or AI, and again, that's an important element for us. One of the things I concentrate a lot, being as I'm looking at cyber, is what is the failure mode of the system that you're looking at, and particularly the machine learning, the AI. And also, because I often end up in court, having to account for what people have done or not done, what is the standard type of evidence that's going to be required for your machine learning system? And I've put at the bottom there a brief sort of definition that I work with all the time. Systems resilient if and only if there's justifiable and enduring confidence that it will function as expected when expected, which was my way of summarizing what I'm looking for. It tries to encompass the through life aspects of these things, but it also teases out some of the questions that I find to be difficult. How do you actually have confidence? What is that confidence based on? Why is it actually justifiable? So those are the sorts of things I will try and talk about, which I hope will be of some interest to you. And I'll look at these in terms of what are the different economic benefits and disbenefits of security approaches in engineering-based and often regulated industries. So things such as factories and OT department, OT that you actually get in those have quite stringent security requirements in relation to the time that things must activate, the amount that you actually get in relation to this. You have serious implications in terms of uptime. So you can't be forever losing the capability to manufacture, for instance. The implications that are often for skills and power consumption and safety criticality are often overlooked when people are looking at what it might mean in terms of AI and the outcomes that you might get from that. Complex supply chains, so looking at the different things in relation to that, so IP suppliers, product suppliers, system integrators, those sorts of things in relation to that, and looking at whether actually these things mean the same thing at each point. So one of the things that I guess has driven me is the state of the art is starting to be costed and monitored through life life on and off board product cyber management plans, and the unaffordability of cyber is a major factor in delayed products, and we've started to see that from 2023. So the difficulties of actually bringing things forward to market because of some of the regulations that we've seen coming in, and some of the implications, not necessarily cyber regulations. There are very few of those still around, but actually those latent regulations in relation to safety or availability, some of the telecoms things that you actually get in relation to this. And I've tried to put up here a slide that was designed to actually capture my problem. And obviously, it's always hard to put things onto one slide, so I've tried to put this onto one slide. really showing that what I'm actually looking at is a complex hyperconnected bottom-up system with emergent properties for which there is no guiding mind. And that to me is something that is different than we've been trying to do before. And part of the reason for putting this up is because it's often suggested that if we did a bit more, if we worked a bit harder, we'd be able to actually get things working. And AI and machine learning are fitting into these things. But what I really wanted to draw out is that from my understanding, chaos and emergence are two fundamental characteristics of complex systems of this type. If I look at the work that I was doing on 5G systems, for instance, the use of machine learning and AI to actually control the beamforming and things of that nature is an entirely attackable area. It's an intensely complex set of things in relation to that. And it gives implications not just for the system itself, but for those things that might be dependent on that system. So I've tried to put those sorts of things. And in the context of this, we try and look at how we can maximize performance, we can minimize harm and damage resulting from faults, failures, attacks. We have to provide the evidence for regulatory compliance. And normally what I talk about here as well is there are different requirements. So if you look at criminal responsibilities that you might have in relation, they are different, and they often occur at the level of, for instance, a critical national infrastructure supplier or somebody of that nature. But the products that go off into that are often just looking at contractual responsibilities. So the things on which you're basing things there are providing different types of evidence. Some of those, and they're going to different types of courts that you might want in different laws around those sorts of things. This idea that it's impossible to actually remove all the faults and failures from a complex dynamic system, I think, is an important point there. So generally speaking, what we try and do is talk about the computer science theory, the mathematical theories that actually sit behind these things, and the evidence that there may or may not be around this, and how does actually AI and machine learning fit into these things. So essentially, beyond a simple system, we are not actually able to enumerate all of the cases that might go with these things. So by a simple system, I mean a few lines of code. So these systems that are hyper-connected to get your effect, which are entirely beneficial, are actually beyond the limits of what we're actually able to state things about. And that means that it's impossible to prevent all cyber attacks. So it means that you need to be looking in different ways. If you're expecting these things to fail, then you must be expecting that you will be able to control the harm that comes out of these. So there's a vocabulary that we need to use, which is often not well understood, which is one of resilience and is one of understanding for how these things actually go together. And this requirement to be able to recover is actually, I think, a fundamental element in actually being able to evaluate, are you spending the right amount of money? Are you spending it in the right places? And will you be able to provide justifiable evidence of what you're actually trying to do in relation to this? So looking at the risk factors that were associated with these things, what we try to look at around this and is the sheer complexity of how these things might actually fit together. And from my point of view, we've essentially done a thing, and I like computer science. I like proper theories that sit behind things. So what we've actually tried to look at is how do things fit together and what are you able to do? So what we set out to do is to demonstrate that every instance of a cyber attack could be seen as an emergent property of a complex system, which is interesting because that actually means that we're able to start to apply some science to these things rather than playing whack-a-mole with the outcomes that come from these sorts of things. It means that you can start to talk about what you're actually able to do and what you're not able to do in relation to these types of systems. So going through this thing, merely looking at the risks and how they actually fit together, this is an intensely complex environment to be trying to fit into. And the complexity and the vulnerabilities and the regulatory environments. And we're increasingly seeing, particularly in the OT environment, in the telecoms environment, that the that the keenness to regulate on some of the products and things that you're now basing this on is actually forming a major vector of attack against the products that we're looking at. One of the things I'd like to highlight for you in relation to this is the difference between complicated systems and complex systems, which we use quite a lot in our analysis. Complicated systems are those where if I wait, I'll get a slightly more powerful computer, I'll be able to work it out. They do not have these characteristics of emergence. But complex systems, I believe, is where we are. And those are the ones that do have these emergent properties in relation to this. That, I think, you need to think about when you're actually considering how will I defend and what will I want to be able to say about my system. Yeah, so this idea of how things fit together, one of the studies that we looked at in relation to this is the unaffordability of cyber defenses in the way that we're trying to do them. You know, essentially, if you say that complexity is the major consideration that you have in relation to that, and that is growing by anything between 4 and 10% per year, depending on which industry you look at, that is an exponential curve. There is no particular reason why you believe that's going to reduce, and that looks like something that is actually not going to be something that you can actually counter as you go along. And what we try to identify as we go through here, and I will not pause on these particularly, is that things like your normal engineering approaches, those that use for cyber, are actually making it impossible to counter the types of attacks that you would be seeing in relation to that. I don't want to pause on this one, I'm sorry. But we did try and work out what AI meant in relation to that. Yeah, so this idea that actually it forms part of the complexity that goes with this thing, that in fact it's not different, it is inherently in the same characteristics of the sort of thing that we're trying to do this, and its application to real world problems. So we think one of the things that are important is to actually look at where are you in relation to this and where might you employ this. So if, for instance, you deploy your AI system in order to counter every attack that comes, it is not clear that it would ever be able to do that. It's not scalable to do those sorts of things. If, on the other hand, you were to deploy your AI system or your machine learning in order to determine where you might, how you might find holes in a model or something of that nature, that is an entirely appropriate thing. And that goes with some of the use that we're seeing in relation to that. So just dropping through on this one, because I wanted to leave a couple of slots for questions. Yeah, so is it different from regular complex systems? Actually, no, it isn't. Beyond the fact that we actually understand so much less about what it's supposed to be doing in the first place. And am I using it where the limits are appropriate? That is a really important question to ask, because in many cases you're not. We're using it in places where it doesn't work. Do I understand the failure modes? Almost certainly not with the machine learning AI system, and particularly if it's integrated into a complex system. And is it generating evidence of a standard and type that I need? Well, given the above, it's actually extremely difficult to work out what type of evidence it is generating. So I think that is where I think I would like to finish my talk and move on. Thank you.
Thank you so much, Peter, for sharing your thoughts. We have about a little over 4 minutes here. So I want to ask, you talked about the different incentives through supply chains. How big of a problem is this?
Actually, I think that's a really significant problem, because I think very often people talk about security or they talk about functionality as though there's just one thing. But I think very often what you've got is different parts of your supply chain are fundamentally incentivized to do different things. Mm-hmm. So if I'm a product supplier, I'm incentivized to prove that my product does exactly what I said it was going to do. However, if I'm supplying a system with a machine that could harm people, then actually I'm responsible for the outcomes of that, not just proving that it did what it. So I think those differences between that are underestimated at our peril and are really, really quite important.
Okay. And if we zoom out a little bit and think of the big picture, do you think AI is force for good or bad in the emerging end-to-end communications technologies?
I personally believe it's a tremendous force for good. However, it's the same as all of these things. It's a tremendously powerful tool. And if we're using it in the wrong places, then we will get very bad outcomes from that. And I personally believe that one of the things that it's doing is it's replacing human beings who would make individual decisions. So it's essentially meaning that we are much more likely to get systemic errors in our systems when they go down. And that has a much greater potential for harm. It has a much greater potential for non-availability and things of that nature in relation. So I think it matters a lot where we use it. But if we use it appropriately, it's absolutely critical. And in some industries, it's absolutely impossible to do without it.
That is true. And do you think that the lack of consistency in the way we discuss AI is a serious problem?
Yes, would be the short answer in relation to that. So I think people talk about whether there's AI or not AI, but for instance, what we see is AI appearing at various different places. We see it appearing in products. We see it appearing in the systems that are using those products and the sensors that we have. We see differences between machine learning and various other parts of AI. We see people who've come across ChatGPT and things of this nature. There are fundamental differences between those, and yet people are talking about them as though they're all the same. And it's clear that just isn't the case. So that aspect of understanding how they fit together, and from my point of view, as somebody that's trying to defend these systems and defend against cyber attacks in these sorts of systems, what's evident is that the lack of understanding about what type of AI and what you're using it for is meaning that people don't necessarily have the skills for the outcomes and the things that people and society is relying on them to actually write. So we did this in a braking system where there were 23 sensors, with all of which had machine learning, and nobody actually discussed this as a potential problem from a safety point of view. But nobody had any difficulty in understanding that a braking system is definitely a safety critical component.
Right.
So that I think is absolutely why I see this as a problem.
For sure. And so do chained virtualized networks cause security issues, and how are those mitigated? If you can just answer that in a few seconds. That's one of the questions we got from the audience.
I think they absolutely could. Yeah. So I think one of the things that is often forgotten is that networks have different outcomes, different things that they try and defend, and different positions they go to under failure. And when we're talking about attacks and secure networks, what we're talking about is where do you go to under failure? So looking at networks that may be controlling machines, I absolutely can't have them stop in the event that I have a failure. Looking at things that are primarily looking at privacy, I absolutely want them to stop. Chaining those things together now means that what actually ripples up is the problem, and we don't really discuss that. And I think we need to.
Okay. All right. Well, we're running out of time here. Thank you again, Peter, and thank you everyone for joining us for the Industrial Wireless Forum. I'll see you at a later session. Stay tuned.